Hi everyone, welcome back to MATA02. This is the end of week 4, and this will be our last completely virtual day of lecture. So next Monday we will be going back to in-person if all goes well. So fingers crossed. Let's see. So today we are going to be talking about the Fundamental Theorem of Arithmetic. So that sounds like a really big deal, and it is a really big deal, but we've seen all the building blocks for it now. And in fact, the Fundamental Theorem of Arithmetic is just all about building blocks. That is, in fact, all that there is to the Fundamental Theorem of Arithmetic. It's about these multiplicative building blocks that we've been using, the prime numbers. So that brings us to our central question, right? What kind of building blocks are the prime numbers? Are they more like Legos, discrete and separable, or are they more like paint colors? Once you've mixed them, you can't separate them anymore. So, which of those are they? So, like, when you have different building blocks, like you have the primary colors of paint, so those you can use to mix together and you can paint all kinds of things, or you have Legos, which you can put together and take apart, and they remain discrete somehow. Okay, so it looks like most people are saying they look a little bit more like Legos, where they're separable and discrete even after you've like jumbled them together by multiplication. And the answer to that is, indeed, yes. They are, in some ways, more like Legos, which are separable and discrete, than they are paint colors. Yeah, because you can always break them up, which I think, yeah, Tiffany, you're absolutely right. You can always break them up. And so you get things like 60 is equal to 2 times 2 times 3 times 5. And so, because you have this factorization, you can both put them together and break them apart. They're really a lot more like Legos. But, okay, so let's continue this Lego analogy a little bit and think about like all different things that might make things more or less like Legos. So you guys might see I built I didn't actually build anything interesting. I just threw together a couple Legos I had. So we have I have this Lego structure here. And so suppose I have this Lego structure here. If I divide this Lego structure into 2, can I separate the yellow part? Just a moment. Let's put that on yes. Let's zero out my chat. And let's zoom in a little bit. So I have this Lego structure here. If I were to subdivide it into 2 different structures, can I separate the yellow part? So I'll just rotate it a couple times. Now, if we were there in person, I would actually have Legos there, but unfortunately, we still aren't quite in person yet. So let's see. What do people think? Okay, so some people think yes, but well, let's try separating it apart. And one of the things you'll notice is that, unfortunately, this here is not. This is just a single piece. So this piece here, actually, you can't separate into 2 parts because this yellow part, because it just happens to be a single piece, right? So this single piece is somehow fundamental to Legos. I cannot separate this because of the way it's structured. Okay, so let me put this back. Okay, but what about? Let me reset again. What about looking at the same structure? I've now reconstructed it. What about the gray part? Can I separate that? So A for yes, B for no. Okay, so A for yes, B for no. Let's zoom in a bit just so you can see it a little bit more closely. Oh, sorry, my ring light is really reflective on the Legos. But yeah, so the answer to this is, well, because this is actually the gray part here, I mean, you could separate in such a way that it's a single piece, but it's actually built from 2 pieces. And so if you divide this entire structure in half, you can divide it so that this gray piece comes apart, because it isn't a fundamental single piece. Instead, it's 2 pieces that I've jumbled together. And so, for those of you who've played a lot with Legos, that should seem a little bit obvious, right? Because you have very few Legos that are like 2 pieces high, um, roughly speaking. But now, sometimes it's a little bit harder to tell because sometimes when you put them into this bigger structure, pieces that, especially same color pieces, might get a little bit mixed together. So if we, so my next question is, what about the red part? So, red part, let me zero out the chat before you respond. So what about the red part here? Can you separate it? So let's zoom in a bit. Well, I've sort of let in, and let me see if I can get the angle right. So, can you separate this into 2 pieces? Okay, so a lot of you did manage to notice that there is actually a little dividing line there, and what that means is I can break it up into, oh, sorry, I started with, even if you didn't have this other red piece, sorry. Even if I didn't have the other red piece, you still can take this here and separate it so that one of the red pieces on one side and the others on the other side. Because these were 2x2 blocks starting out, and not actually a 2x4 block. Okay, so that, and so when you're looking at prime numbers, like you get very similar properties to these sorts of Lego pieces. Sometimes, let's go back to my PowerPoint. So individual Lego pieces can't be split in half. So like if I had this red piece here, which is just a single piece, you can't split that in half. But if you have these red pieces, which aren't just a single piece, combinations of Lego pieces can, of course, be split into pieces. And sometimes it's obvious that you can split them in half, but sometimes it's really not obvious. Like if I were to hide this red piece in the middle of a structure like this, then it would be really hard to tell that this red piece is actually 2 pieces unless you catch the light exactly right and see the little dividing line. Okay, so that is one of the basic ideas about using Lego structures as Legos as building blocks. So now, what is a prime? So we talked about Lego building blocks. Let's go back and talk about, well, building blocks that are the multiplicative building blocks of the natural numbers, the prime numbers. So a prime number is divisible by only 1 and p. Remember, that's how we define these things. And so, for example, you have something like a prime p. So one way of defining it, let's say the number 5, which is prime. So number 5, well, the one way of doing that is you check if 5 divided by 1 is equal to 5, 5 divided by 2 is not equal to a whole number, that's equal to 2 and 1/2. 5 divided by 3 is equal to 1 and 2/3. 5 divided by 4 is equal to 1 and 1/4. And 5 divided by 5 is equal to 1. Okay, so it's only divisible by 1 and 5. Now, of course, we showed last time that you don't actually have to check every single number. You can just check the primes, and that'll also tell you if it's a prime number. And you only need to check the primes up to the square root. But in essence, like overall, what we mean by a prime is something that's divisible only by 1 and by itself. Whereas a composite number, like 6, well, 6 divided by 1, it's still also always divisible by 1. And, of course, it's divisible by itself. But we also have it's divisible by some other numbers. Like 6 divided by 2 is 3. 6 divided by 3 is then 2, of course. 6 divided by 4 is actually 1 and 1/2. And 6 divided by 5 is 1 and 1/5. Okay, so prime numbers are divisible by more different things. Okay, but that's not the only way of understanding prime numbers. Another way of understanding prime numbers is that they're the smallest set of multiplicative building blocks needed to generate all the positive integers greater than 1. So let's write out a few of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, we ignore 1 because 1's special. And then, well, 10 is 2 times 5, so you don't need 10. 9 is 3 times 3, so you don't need 9. 8 is 2 cubed, so you don't need 8. And 6 is 2 times 3, and 4 is 2 squared. So with this smaller set of multiplicative building blocks, you can generate basically everything. So let's take a look at another consequence of primes. And so I'll be asking you for intuition, and then we'll be going through and carefully proving this, or carefully showing that this is true later. So what's another consequence of primes? And you can think back to our Lego building blocks as an analogy. So when is a product of two numbers, a and b, even? Is it when a is even? Is it when b is even? Is it when both a and b are even? Is it when a or b are even? So either one, or is it none of the above? So notice that when I say when both a and b are even, that means that, so what is the most general possible answer is what I mean here. So, and when I say the most general possible answer, I mean, do you need both a and b to be even, or do you just need one of the two to be even? Because 3 times 2 is equal to 6, and 2 times 2 is equal to 4. So in this particular case, you have to be a little careful about how mathematicians refer to numbers. So it is certainly true that when a is even, the product is even. When b is even, the product is also even. When both of them are even, you also get an even number. But when even just one of them is even, you get an even number. Yeah, exactly. So 9 times 2 is 18. So notice that you don't need both of the numbers to be even. You only need one of the two numbers to be even. So you have things like 2 times 5 is equal to 10, and 7 times 4 is equal to 28. So you only need one of the numbers to be even. So this is the most general answer, though obviously it is also even in each of the first three cases because D contains all of the other three cases. Most general answer. Okay, so, well, now we've done that. Let's do another one. What about, let's zero out the chat again. What about a product AB of two numbers? When is a product of AB of two numbers A and B divisible by 3? Is it when A is divisible by 3? Is it when B is divisible by 3? Is it when 3 divides, that should be a both there. Both A and B, or when 3 divides either A or B. Okay, yeah, so this is, yeah, it'll be a multiple of 3 with just one of the two, when 3 divides either A or B. And so D is indeed the right answer here. And we can see this in a couple of examples. So for example, 3 times 5, well 5 is clearly not divisible by 3, but 15 is. Or 7 times 9, well 63 is divisible, 9 is divisible, but 7 is not divisible. Okay, so somehow the analogy here is that if you're looking at a Lego like this, if it's a prime number, well, I got getting ahead of myself. Let me ask one more, and we'll see what people say. Well, I may have given away the punchline. So what about the product AB of two numbers A and B divisible by 6? Is it when A is divisible by 6, when B is divisible by 6, when 6 divides A and B, when 6 divides either A or B, or none of the above? Okay. Well, think about this a little bit. Oh, could you resend the website? Yes. Okay, well, then let me propose asking you a question. What is 4 times 9? And is that divisible by 6? Yep, 4 times 9 is 36, and that is divisible by 6, and neither of the individual pieces is divisible by 6. Okay, what's the difference? And given what we've been studying, like, the difference should be something that you can guess, right? Yeah, exactly. Katie is absolutely correct. 6 is not prime. Yeah, 6 is a multiple of 2, and it's a multiple of 3. And so what happens is that we have one copy of 2 here, so this is 2 times 2 times 3 times 3, and because 6 isn't a base building block, you can rearrange it so that you get a 6 out of that combination. And so we can give an analogy to Legos here. Let's see, let me go ahead and switch over to my next slide. So a prime is a basic building block you can't separate, like this yellow piece here. So this yellow piece that I'm holding up to the camera, you can't separate it. And so no matter what you do, if you have that yellow piece in your structure, so if you put that yellow piece in the structure, whenever you break that structure up, one of the sides of the structure has to have the yellow piece, because it's a basic building block. But on the other hand, this red part here, like this red structure, so this 2x2 red structure, even though it looks very similar to the yellow piece, it's actually made from 2 smaller pieces. And so when I divide up the structure, my 2 red pieces can come apart. And so 6 is more like these 2 red pieces. It's actually built from a 2 and a 3. And so when you divide up a bigger number, the number that you're dividing into 2 parts by division, you can break up the 2 parts. You don't have to, but you can. Does that analogy make sense? So this is one of the other reasons that prime numbers are so important, because somehow they're not just the smallest set of building blocks, they're a set of building blocks that you can't subdivide even further. So like, once you've divided down the primes, you can't break a prime up into smaller pieces. Any questions about that? Okay, but yeah, so like, this is why prime numbers are so important, is because they're the basic Lego pieces of multiplicative natural numbers. So, whereas composite numbers are cool and all. You can build really cool structures, and in some ways, composite numbers, there are some ways in which composite numbers are more interesting because you can build all kinds of interesting things with them. Like this entire thing you can think of as a composite number, but they're not the basic building blocks. And so when we're studying what is a Lego or what is a prime, one of the things you might want to look for is not the complex building blocks, structures you can build, but the pieces that you're using to put it together. Okay, so enough analogizing. Let's actually show some of these things. So like what I did a moment ago is I gave you a couple examples, and I was like, well, 6 can be broken up and 3 can't. But is this actually true? Can we show ourselves that this is always true? So one way to show ourselves that things like this are always true, well, is to try to directly check. So later we'll get to a proof, but you can try directly checking. So how can we convince ourselves? So not like prove to ourselves, but just convince to ourselves that something like this is true. Well, one way is to check every number divisible by 3, and then we just check each combination of divisors. So maybe we're up to number 60. So how would we check that this is true for 60? Well, we know 60 is divisible by 3. And so then what we'd have to do is we'd have to separate out and get each combination of divisors. So 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times 12, and 6 times 10. And this turns out to be all the different ways of breaking up the number 60 into 2 numbers. And, well, we can check. Is 1 divisible by 3? No, 1 is not divisible by anything except 1, but 60 is divisible by 3. And 30 is divisible by 3, and 3 is divisible by 3, and 15 is divisible by 3, and 12 is divisible by 3, and 6 is divisible by 3. So this is true. So, like, you can check that 60 is a number that's divisible by 3, and at least one of the 2 pieces that it breaks up into is divisible by 3. But this is a little bit slow, right? So if you want to do this, you have to do this for every single multiple of 3. So 63 is equal to 1 times 63, or it's equal to 3 times 21, or it's equal to 7 times 9. And you can check, and you can see, oh, well, 63 is divisible by 3, 3 is divisible by 3, 9 is divisible by 3, and so that works. And if we keep on going, let's see, what's the next number divisible by 3? 66. It's equal to 1 times 66, or it's equal to 2 times 33, or it's equal to 3 times 22, or it's equal to 6 times 11. And then we can check again, so there's 66, 3, 33, 6. And so that works. And we can keep on going, and you could in theory do this for lots and lots of numbers, but this is kind of slow, right? So this would be a really, really slow way of figuring out that that's true, and then you'd still never get done because you have an infinite number of numbers. It would still take you a long time even to check just the finite amount of them. So does anyone have any ideas about what else we can do instead of doing the sort of direct checking of the product? What else could you check instead? Okay, so I'll go ahead and tell you the answer, since it's a little bit subtle. But the other thing you can do is you can check the opposite. You can check the opposite. Instead of checking if you have a number that's divisible by 3, if it breaks up into two numbers divisible by 3, you can just check to make sure that if a number isn't divisible by 3, and when you multiply them together, it's still not divisible by 3. So if you check every combination of that. But then you only have to check the divisibility by 3 of AB each time you multiply things together. And so one way of doing that is to have a times table of all the numbers that are not divisible by 3. So I'm noticing a lot of people voting E for some reason. I guess you're just catching up on the vote. So anyway, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are our numbers, but let's ignore 3, 6, and 9. Since we don't want to check things that are divisible by 3, we just want a times table of all the other numbers. So let's see, 1, 2, 4, 5, 7, 8, and 10. Okay, so we can write up this times table. And so what do we get? We get 1, 2, 4, 5, 7, 8, 10. Oh, sorry. We get 2, 4, 8, 10, 14, 16, 20, 4, 8, 16, 20, 28, 32, 40, 5, 10, 20, 25, 35, 40, 50, 7, 14, 28, 35, 49, 56, 70, 8, 16, 32, 40, 56, 64, and 80, and lastly 10, 20, 40, 50, 70, 70, 80, and 100. And so once we've re-explained, oh yeah, so we have a question about can I re-explain the last point. So the basic point of the last slide is that one way is just you can check if things are true for a bunch of numbers. But this is really slow because for each number you have to check each of the ways it divides up into two numbers. On this slide, we're instead doing the opposite. We're checking that if both A and B are not divisible by 3, then the product is also not divisible by 3. So basically, we're just trying to check if you have a number that has 3 as a building block. So if you have a number that has this yellow piece as a building block, whenever you divide it up into two different pieces, it will still always have this entire yellow piece as a building block. Where the yellow piece is an analogy for the number 3, which is a prime number. Yeah, and so we can also check this opposite. So you notice that whenever you multiply together any two numbers that are not divisible by 3, you can check all these numbers are also not divisible by 3. So neither of these things are proofs. One of the things that I should emphasize is that you probably think of like proofs as like one of the central, really confusing, abstract things about mathematics. And it is that. But why do we, but how do mathematicians come up with what we're going to prove? So like sometimes in a high school geometry class, you might have been told, prove that the angle, that if you have a parallel line and you have the angles in a certain way, that these two angles are the same. And that is like the process of arguing that something's true. But how do you know what's true to begin with? And large part of what mathematicians do is we just play with numbers, we play with ideas, and then we get some sense of, well, this weird thing seems to happen a lot. Maybe we think it's true. And one of the things that we're guessing now is, well, maybe if something is divisible by 3, then whenever you break it up into two pieces, at least one of the two pieces has to be divisible by 3. And now that we have this guess, we can try to prove it. All right, so it's sort of like we have a hypothesis. We have some hypothesis, and then we want to prove it after we figured out what the hypothesis is. So often in math classes, one of the issues is that people just tell you what to prove. And this, but a larger part of mathematics is figuring out what you ought to be trying to prove. Having said that, I have now shown you what we want to try to prove. So let's go ahead and prove it. So let's carefully prove it. And I will tell you in advance that I will be asking you in chat participation about this proof. So make sure you follow each of the steps. And I will try to go slowly, but ask questions because I will have a chat question that requires you to understand the proof in a moment. So let's consider a product AB divisible by 3. Okay? So we want to show that at least one of A or B is then divisible by 3. So let's consider the first case. So suppose 3 does not divide A. So what are we trying to prove if we're going to start with the idea that 3 does not divide A? Well, what our goal is to prove that at least one over A or B is divisible by 3, right? So I'm noticing that, so just as a random note, I'm noticing that people are throwing random letters into chat, like from time to time. If you have questions, please just ask, since I don't actually know what you mean when you just throw an E into chat. If you're going to throw random things in chat, like when I'm not asking a particular question, it probably makes more sense. Oh yeah, it might be a glitch. Yeah, okay. You might need to refresh the page at some point. So apologies for that, if there is a weird glitch that's going on in there. Yeah, no, since it is the same people who are... Yeah, so that does look like a glitch. So I apologize for that. That's probably my fault. But yeah, anyway, so suppose 3 does not divide A. If 3 does not divide A, then what do we mean by... what do we want to show? Well, what we want to show is that then 3 divides B, right? Because we want to throw 3 divides at least one of the two pieces. So we want to show that 3 divides B. Because if we can show that if 3 doesn't divide A, then it divides B, then we're done. So how do we show this? Well, let's say we know that because only 1 and 3 divide 3, since 3 is a prime number, the greatest common divisor of 3 and A is equal to 1. It is either 1 or 3, right? Because it has to be a divisor. In the including item, one of the numbers should be divisible by 3, right? We haven't quite got to the Euclidean algorithm yet. We haven't used it yet. We're just making an argument about divisors right now. But yeah, so if we just wanted to find the greatest common divisor of 3 or a, we know the answer to that has to be a divisor of both 3 and a, right? And 3 only has 2 different divisors, 1 and 3, and therefore the greatest common divisor of 3 and anything else has to be either 1 or 3. But you'll notice that we also know that 3 doesn't divide a. So we can actually rule out the 3 because 3 does not divide a. Right? That was one of our original assumptions in this case. So we know that 3 does not divide a. So now here is where we use the Euclidean algorithm. So we have now just shown that the greatest common divisor of 3 and a is equal to 1. We didn't actually do the full Euclidean algorithm to show it because we don't know what a is, but simply by the fact that 3 is prime and 3 does not divide a, we now know that the greatest common divisor of 3 and 1 is a. 3 and a is 1. So we can now use the reverse of the Euclidean algorithm. So reversing the Euclidean algorithm, we can rewrite 1 as equal to x times 3 plus y times a, where x and y are also whole numbers. Right? Remember, that's one of the things that I have you do on the quiz. That's one of the things that... so I actually make you do all the steps of it. But whenever you use the Euclidean algorithm to get the greatest common divisor of two numbers, you can reverse it and then say, well, that means that we have some way of writing the greatest common divisor as a linear combination, as the integer linear combination of the two numbers you started out with. Okay, so this is reversing the Euclidean algorithm, and yes, it is many steps, but because we know how to use the Euclidean algorithm, we're just going to skip all those steps and just say, well, we know that it's equal to something times 3 plus something times a. And something times a. Did everyone follow? That was a sort of tricky jump of logic there. Okay, so hopefully everyone followed. So we're basically so on the quiz part, question 3, I have you do two parts. One part is you do the Euclidean algorithm to find the greatest common divisor, and the other part is you can use that and reverse it. Yes, this is exactly part 3.2 of your quiz. Yes, this is exactly that. You can reverse it to go backwards and then find the greatest common divisor as a linear combination of the first two things. And this is super important here because x and y are unknown. So x and y are unknown integers. And the way you'd solve this is you would do the reverse Euclidean algorithm. Right? So this is I'm not carefully solving it here because you don't actually know what a is. But if you had any particular a, you could reverse it and solve it, right? So that's the entire point of the part 3.2 on the quiz, is that once you know the Euclidean algorithm, you can go backwards. And so we happen to know what the answer is. We know that the greatest common divisor of 3 and a is equal to 1 because of our logic above. And so even though we didn't take all the forward steps, you know that if you had any a, you could take all the backward steps. Okay, so let's keep on going. Well, now we have this equation. Let's multiply the entire equation by b. Right? So we can, of course, multiply both sides by b. So you end up getting b is equal to x times 3 times b plus y times a times b, right? But now notice, once you've done this, that's a multiple of 3, right? And this a times b is also a multiple of 3. Because of our original assumption that a times b is divisible by 3. And therefore, this entire b has to be divisible by 3, because the two pieces are both divisible by 3. So then that implies that b is divisible by 3. Okay, so what we've just shown is that if A is not divisible by 3, but AB is divisible by 3, then clearly B must be divisible by 3. Okay, so now I know I walked through that a bit slowly, but this is sort of important proof, and so I wanted to go through it a bit slowly. Well, let's go ahead and conclude the proof. So the basic idea is if we assume that AB is divisible by 3, then in case 1, A is not divisible by 3, then B is divisible by 3. What would case 2 be? So if case 1 is we're going to assume A is not divisible by 3, what would be the other case? What's remaining? Yeah, so the case 2 is A is divisible by 3. So case 2, in case 1, you're considering the case when A is not divisible by 3. In case 2, you're considering a case when A is divisible by 3. But these are the only two cases, right? So either A is divisible by 3 or it's not divisible by 3. It can't be somewhere in between. And therefore, in both of the cases, at least one of the two is divisible by 3. So therefore, if AB is divisible by 3, then at least one of A or B is divisible by 3. Okay. So now that we've done that, what if we replace something in the argument? I'm going to reset the chat now. So what happens if we replace 3 with 5? Does the argument still work? Okay, so we have most people saying yes, a few people saying no. Okay, fine. Most people are saying yes. That is indeed correct. Maybe because it's also a prime number. Well, yes, that is exactly the reason why it still works, and we'll see that in a moment when we see what happens when we replace it with something that isn't prime. So let me zero out the chat again. What if we replace 3 with 6? Does the argument still hold? Okay, so I've sort of led off with like telling you the punchline, and so it is indeed true that if you replace 3 with 6, then the argument doesn't hold anymore. But why is that? So what goes wrong when we replace 3 with 6? And before people respond in chat, though, you can go ahead and respond in chat. What I'm going to do is I'm going to go back to this slide. Well, yes, it is because 6 is not prime. But where do things go wrong? So does it go wrong in this step? What about in list step? Or maybe list step, or maybe list step, or maybe list step. So clearly your argument has to go wrong somewhere. So what part of the argument does this go wrong? Okay, so we're getting a lot of B's, a few C's, and 1 or 2 D's. So what is true about something that's not prime? Or rather, what is true about a composite number? Yes. So we have Katie who's answering B because not only 1 and 6 divide 3. Exactly. So if you were to replace this with 6, you get 1, 2, 3, and 6 divide 6. And so that's where that argument goes wrong, because it can be broken down into smaller numbers, and then all of a sudden, once you have multiple, multiple numbers that can divide. Oh yeah, once you have multiple numbers that can divide the number that you're trying to say everything's divisible by, then the next part of the argument also doesn't hold, because then we know 6 doesn't divide A, but 2 or 3 might still. And so because of that, you can't use the reverse Euclidean algorithm because you can't break it up into, you don't know what the answer to it yet is. So when the number that you're dividing by is prime, then you know what the greatest common divisor of it and any other number that isn't divisible by it is. It's 1. But if it's not prime, then you don't know that answer, and so you can't use the reverse Euclidean algorithm to figure out what it actually is. Okay, so I know some people have asked me before, am I going to make you write proofs? And the answer to that is Probably not. Writing proofs is really hard. But I might make you on the midterm look at a proof and then try to figure out what went wrong. So this is the kind of thing that writing a proof from the scratch is really, really hard. But figuring out where the logic breaks down, that is something that I might ask of you. Okay, but anyway, let's keep on going. I seem to be going slower than I normally expect, but that's all right. That's fine for this class. When is the midterm? I'll talk about that in the break. So logistical announcements I'll put in the break since I want to keep on going with this proof right now. So remind me again in break to ask. It's also on the course calendar. Okay, so what we just did is we just finished this proof, and we showed that this proof works for any prime number, but not for any composite number. And that is, of course, brings us to our punchline, which is that, if a prime number p divides a product of numbers, then it must divide one of the factors. So, for example, we know that I can show you that 7,623 divided by 7 is equal to 1,089. And so it's divisible by 7. Well, and that means that if I were to write out 7,623 is equal to a product of 11 and 693, then even without doing any division, you automatically know that 693 is a multiple of 7. Okay? And so that's what you can get from this theorem. We just proved a theorem. Okay, so let's have you guys try it out for a really complicated one. So let me reset the poll. So let's have you all try it out. So let me go ahead and tell you that this big ugly number, which is 1,089,746,112, I am just going to tell you that this is divisible by both 91 and 97. I am also going to tell you that this number is also equal to the product of 436,597 times 2,496. So now, without doing all the divisions, which of these facts are true? So at least one of the two things is divisible by 91. At least one of the two things is divisible by 97. Both A and B are true. Neither A or B nor B is true, or none of the above. So I notice a lot of you have answered, but let me remind you that when is that theorem true? The theorem that's at the top of the slide, when is it true? When it's a prime. Yes, it is only true if it's a prime. Are 91 and 97 prime numbers? Yep, bamboozled again. So, you need to be really careful when I give you a number. And yes, I gave you a sort of harder set of numbers here. So, are both of these numbers prime? Or maybe is only one of these numbers prime? Or maybe none of them are prime. So don't worry. Like, I meant to trick you guys there. But I meant to... So, if you look back on our previous notes, you'll notice that if you look back on our previous notes, you'll notice that I wrote down a list of all the prime numbers from 1 to 100. And if you notice on there, 97 is prime. That is prime. But 91 is not. 91 is equal to 13 times 7. Yep. Yeah, and so like that is in many ways one of the harder numbers to figure out isn't prime. So just be a little bit careful about that. It would have been obvious if I had said 6 and 97, but It is sometimes, and I'm trying to make the point that it's sometimes hard to figure out that, is it a trick question? No, it's not a trick question. I mean, I did intend to trick you, but the question has a real answer, which is that only b is true. At least one of these things is divisible by 97. And in fact, I can, so it turns out that 436,597 divided by 97 is equal to 4,501. But yeah, so you have to be a little bit careful about applying these theorems because prime numbers are special. But you have to know that something's a prime number, and that actually turns out to be quite hard. In fact, the fact that that knowing of something is that the knowing that you can break apart a number into like two pieces, figuring out that a number is prime, in general, exactly, is one of the hardest problems in mathematics. So for a really big number, it is really, really hard to figure out if it's prime or composite exactly, to know that with 100% certainty. And it's even harder to then factor it in, like if it's not prime, to then factor it into the different pieces. So in this class, we're only going to be giving easy examples so you can sort of like brute force your way through it. But it turns out that the entirety of internet security is based around the idea that factoring numbers is hard. That prime numbers are special. Okay, but we'll get to that in the very last part of class. So for now, though, let's keep on going, and we can let's give a smaller but just as important result, which is we finally can talk about the fundamental theorem of arithmetic. Oh, we have a great question. So do hackers have to find the primes, though? Yes, sometimes they do. And in fact, that's one of the ways of breaking internet security is to... so I'll go into this later, but one of the things that you can do, if you could take a number that isn't prime, if I have a number that is a product of two really big primes, and you can tell me what the two primes that make it up are, and you can do this in general for really, really big numbers, you could break a large part of internet security. But yes, that'll be the end of class, so that'll be the punchline. When are you going to get to the hacking lesson? Well, we're going to get to the encryption lesson at the very end of class. That is the sort of end goal of this class. Not next week. Not quite yet. But anyway, so we're going to be building up with smaller things because it turns out that that is a big result. And so this here is a big result as well, but it's not quite as big. So in fact, I've already talked a little bit about the fundamental theorem of arithmetic. We mentioned this when we talked about factoring. It turns out that any number can be written as a product of primes in one and only one way. So if you can write out the product of primes in one way, you can't write it as some other way. Let me give it, and this has some really important consequences. So as an example, if I gave you the number 14,467 is equal to 17 times 23 times, let's say, that's 37, not 27. So if you happen to know the prime factorization, then I can immediately tell you a couple things. So then I immediately know that 14,467 is not a multiple of 31. Because of course 31 is prime. Well, where n is an integer. N is an integer. Okay? Because 31 is a prime, but then since 31 is prime, if 14,467 were divisible by 31, then you would know that one of the three pieces that makes up 14,467 would have to be divisible by it. So because then one of 17, 23, or 37 would be divisible by 31. By 31 if it were a multiple of 31. And those are all prime. 17, 23, and 37 are all prime. Okay? And so the general proof uses the same kind of logic, that if a prime appears in one decomposition, it has to appear in all of the decompositions, because, well, that's sort of the point of having the prime decomposition. You can't have, if I take a bunch of Lego pieces and I break them apart, the prime numbers, I can't magically come up with a new prime number by breaking them apart a different way. And let me give another example. Let's say another example would be that 60, which is equal to 2 squared times 3 times 5. So 60 is not divisible by 7. Or by 3 squared, which is equal to 9. Because those don't appear in the original decomposition. So, why should we care about this? Well, it turns out that there are a bunch of different ways of writing up numbers, and they all have slightly different properties. So one of the major ways we use to write up numbers is this decimal notation, right? So where the number 10 is special. So for example, 204 is equal to 2 times 10 squared plus 0 times 10 plus 4 times 10 to the 0, because 10 to the 0 is 1. And if you just look at the initial numbers, that's how we get our notation 204. 204, right? And that requires that we use both a combination of summation, so addition and multiplication, and we also make the number 10 special. That's what we call our base. And this way of writing out numbers is really nice because it's pretty easy to see when one number is bigger than another. It's pretty easy to write out pretty big numbers. But it does require the number 10 being special. And now, any of you who have learned anything about how computers store numbers know that you might write it in binary instead, where you use the base 2 instead of the base 10. And so you could also write out the number 204 in base 10 as equal to 1 times 2 to the 7 plus 1 times 2 to the 6 plus 0 times 2 to the 5 plus 0 times 2 to the 4 plus 1 times 2 cubed plus 1 times 2 to the 1 plus 0 times... Oh, wait, did I do that wrong? Did I skip a number? 7, 6, 5, 4, 3... Oh, 2 to the 2 plus 0 times 2 to the 1 plus 0 times 2 to the 0. Okay, so it turns out that those two, that is actually equal. You can double check it if you would like. And then when you write things out in binary, well, you have base 2 instead of base 10. We're not going to spend too much time on this, but it's sort of nice, useful to know. So 11001100 in binary. So that's how computers store numbers, as zeros and ones. And that still also works, but even when you do that, it's still a combination of multiplication and addition, and you have a special number, in that case 2 instead of 10. The ancient Mayans used the special number 60 as their base instead of these. And so, in some ways, there's a lot of choices in how you represent numbers. The Fundamental Theorem of Arithmetic gives a totally different way of writing numbers based on just multiplication and without choosing a special number as a base. So, something like 204 is equal to 2 squared times 3 times 17. We're using a different set of building blocks, and with the prime numbers as our building blocks, we only need multiplication. We don't need addition. So it's a different way of writing things, and those all have pluses and minuses. So, what are some of the disadvantages of writing in factored form? And I'm going to go ahead and give you one that I already said, which is it's harder to know that when a number is bigger. And what are some of the other disadvantages to writing in this factored form? And I've sort of mentioned some of them already. Harder to recognize patterns. So that's a good point. It is harder to recognize some patterns, but is it harder to recognize all patterns? But yes, that is absolutely correct. It's more work. Hard to fathom how the final number works. Using small numbers may take up more space on the computer. Need to expand to solve. Okay, great. We're getting at all of the reasons that this is difficult. So one of them is that converting to a factored form is really very difficult. In fact, that is one of the super hard problems of mathematics. Converting from a factored form to decimal or binary is easy. You just multiply things together. But separating it out, that's really, really hard. Yeah, exactly. So it looks like Maria has too much to build. Yeah, we have a lot more building blocks that we need to work with. So we have to use all the different powers, and that's an infinite set. Instead of just using, all the different primes, and that's an infinite set. Rather than just using, say, powers of 10 and the positions 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And yeah, so there are disadvantages to using prime factorization as well. But somehow, prime factorization is fundamental to like what makes the natural numbers what they are. And that's why they're so important, even though they have these drawbacks that they're a little bit harder to work with. And on that note, I will, that ends this first half of lecture. I went a little bit over the first half, but let's say please be back in 10 minutes time, so at 10:17. And then I will see you in 10 minutes. If you have logistical questions, we can ask them during the break.